All right, we're going to move up to chapter 10 here. I'm going to kind of combine the first four sections of chapter 10 because they all kind of tie into each other. What we're talking about here is how to identify translation and its symmetry and to be able to see what it looks like when you draw it. I'll go through some examples here, then we'll get on the XY table on the graph and take a look at what it looks like and some real examples. But let's get some definitions out first, okay? What is a translation? A translation is when you move a figure without turning it, you're just sliding it, okay? So if this is my y-axis and this is my x-axis, and I just took this parallelogram ABCD and I just slid it over to its new place, A prime, B prime, C prime, D prime, and those are all XY coordinates, okay? I just slid it over, whether I slide it sideways or I slide it down or diagonally, okay? That's a translation. You just slide it, okay? Congruent figures. Congruent means the same size and shape, okay? All the sides have the same measure. All the angles are the same. Everything's the same on they're the exact, okay? What is symmetry? Symmetry is cutting something down the middle and being able to fold it on that crease and have it be equal. It'd be like taking this rectangle right here and folding it over so that it matches up perfectly. A butterfly, when he folds his wings together, okay, and he matches up perfectly. That body that line down the center of his body, that's his axis of symmetry, okay. If you were to fold this right along this line right here and fold it over, everything would match up perfectly. So that's the line of symmetry. You took this triangle and folded it right here across, it would match up perfectly, okay? Whereas you can see if you folded this point down here, it doesn't match up. There's oddball. Things are hanging out, okay? You want it to be able to fold like this and perfectly match up so there's nothing else showing, okay? Symmetry. A reflection. Well, a translation is sliding it. A reflection is like looking in the mirror, okay? It's a mirror image produced by either flipping it over the X or the Y axis, okay? If we had this triangle figure here and I reflected it over, I'm kind of like flipping it over, okay? A reflection is like flipping it over, okay? And I'll show you an example of that on the graph. When reflecting over the x-axis, the x-coordinate stays the same. Like you can see here, when I took point B and flipped this over to point B prime, my x value stayed the same. It was 2 up here, it's 2 down here. But what happens to the y-coordinate is the sign changes by a negative. It was positive 4 here. When I flipped it over, point B became 2, negative 4. So the y value changed signs. The x value, the coordinate here is 2, 4. I'm sorry, 4, 2. C prime would be 4, negative 2. So the x stayed the same, the y changed signs. If you were to reflect it over the y-axis, meaning I went this way, okay, I took it from here and I flipped it to this side, then the x's change, but the y stay the same. Like if this flipped over to here, my x would become a negative 2 and my b would be a positive 4 because I still stayed on the same y line. So whatever line you're reflecting over, the x or the y, that coordinate in the xy coordinate stays the same. The other one flips. I'll show you that. Easier to see in an example. So we got a translation, a reflection. How about a rotation? A rotation is when it's rotated around a point, okay? Neither the size nor the shape changes, okay? If we're rotating this figure around the origin 0, 0, the rotational symmetry is shown here about the origin with a 90-degree angle of rotation. So think of it here. It started out pointing here, and it ended up pointing here. That's a 90 degrees rotation right there, okay? It rotated 90 degrees this way, if you're saying this is the starting point, and this is the finish. If it's here to there, then it's 90 degrees counterclockwise, okay? That's a rotation. A dilation is when you take it and you either enlarge or you reduce the figure, okay? You can see here this figure, right? If you're thinking from small to big, this was dilated big. You get it It's like taking a picture of you. Okay, it looks the same, but it's blown up. We start talking about similar figures instead of congruent figures. Okay, and if you doubled the size, 2 would be your scale factor. Okay, if you shrunk it down by a half would be your scale factor. Okay, so it just depends how you did it. But dilation is just blowing it up or shrinking it. All right, an example. An optometrist dilates a patient's eyes, a patient's pupils, by a factor of 5/3. If the diameter was 5 millimeters, find the new diameter after the dilation. We just take whatever it was times the scale factor, and you get the new diameter. Okay, so because you're taking of the number, now if we know means multiplying in math, so just take your diameter and multiply it by whatever the scale factor is, and then you'll have the new size. Okay, well, let's take a look at some of these on the graph. I'll start off with a rectangle. If I've got a rectangle right here, let me put it over here so you can see it better, and I want to translate it, okay, I can translate it up, down, right, left, however I want to do it. If these are my 4 corners right here, okay, and I want to translate it down, boom, just like that, I can put it anywhere I want. Now it's here. Okay, maybe a little hard to see there, doesn't it? But this right here is my x-axis right here, and this one right here is my y-axis. Okay, there's my y. So I just translate it. You can go wherever you want to go. Okay, it doesn't matter. That's just moving it around. It's pretty straightforward. Okay, if I had a triangle, same deal. I'm just going to slide it around. I can move it right, left. That's a translation. Okay. If I want to reflect it, okay, let's say I've got this triangle right here. If I want to reflect this triangle, then what I'm going to do is I'm going to just take it, and if I'm here on the 3 for the y, I'm going to go down here on the -3 and just flip it. Okay, if I started out, start that again. If I start out right here with this point, I'm on 3 on the positive y. I'm going to go 3 on the negative y down here, and I'm just going to keep that same point, but I'm just going to flip it over. Okay, that's a reflection over the x-axis. Okay, so you notice the y-coordinate changed signs, but the x stayed the same. The x was 2 the whole time. All right, now if I wanted to go the other way, let's say I'm here where my x is 2 and I'm 1 here, and I want to reflect it over the y, I want to go this way, then I'm going to take, this is -2, I'm sorry, I'll take it over to +2, the y value stays the same, and I flip it this way. Okay, so it would look the same. Notice when I flipped over the y stayed the same, but the x value changed signs. Okay, that is a reflection. A rotation, if I started here, you just rotate it around. Most of what we're going to do right now is to rotate it around the origin. Okay, that's pretty much going to be our point. But you could pick any point to rotate it around. But we're just going to move it. Same with here. I can rotate it counterclockwise, or I can rotate it clockwise, however much I want. Okay, I can start here. If I rotated it 45 degrees, and this is my center point, then I would just rotate it. That would be a 45-degree rotation. Okay, because 90 would be all the way to here. And then dilation is just making it bigger, making it smaller. Okay, maybe I had a rectangle that looked like this, and I dilated, made it twice its size. Now it's like this. So it's just making it bigger by that scale factor. Okay, we'll look at some of that in class here over the next 2 days. About translations, to translate it, rotate it, reflect it, or dilation. Okay, we'll get on that when we get back into class here. All right, we'll see you then.